Okay, so in our previous video we talked about sum identities. In this video we're actually going to apply those identities to create what's called a closed form definition for our sigma notation. Now, you might be wondering why in the world do we need to do this for these sigma notations? It's because we have indefinite sums, and typically when we have anything mathematical we want to be able to use the technology, namely we want to be able to graph. And anytime you have an indefinite sum, you cannot graph that the way it's written. So we have to use the sum identities that we learned in the previous video to create that closed form definition, so we're going to be able to graph it, okay? So that's the whole purpose of this video. Again, just like I said in the previous video, these sum identities, it takes time, so practice. If you got questions, please let me know. So let's get started with an example. So we want to find a closed form definition for this indefinite sum of 3k plus 2. This is our sequence, and we're trying to find the sum of that. We're going to create a closed form definition because as it's written, we could not graph this if we wanted to. What we're going to do is create a closed form definition that could be graphed if we wanted to. So let's go get started. Again, one of our identities was when we had the sigma of the sum of two sequences, we can split that up into two sigmas. So let's start with that. Remember, your starting term always stays the same, and your ending term always stays the same. Plus goes in the middle. Again, starting term's the same, ending term the same. The first sequence goes with the first sigma, and our second sequence goes with the second sigma. Not too bad. Now we want to apply the coefficients comes out rules, because 3 is a coefficient and it gets to come on the outside. So 3 sigma, start with the first term, go to the nth term of k. So this 3 on the outside, it's done. It's going to keep dropping down. Now let's go ahead and keep working with this sum as much as we can. So 3 stays on the outside, and we have a rule, if you go back to the previous video, a rule that says when we add up a bunch of unknown numbers, that's called the Think-Gauss identity. So, and if you remember, it was just n times n plus 1 divided by 2. I put it in parentheses, all of it, because I'm plugging in. This sum is now done. Let's go to the next sum. Plus is just going to fall down. I don't have a rule for the sum of a bunch of 2's, but I do have a rule for the sum of a bunch of 1's. So what I want to do is rewrite 2 as 2 times 1, and now 2 can be thought of as a coefficient, and we already know that coefficients get to come out. So the coefficient comes on the outside of our sigma. We're still in the first term to the nth term, and all that's left on the inside of our sigma is 1. Now, our coefficient is just going to keep dropping down, so plus 2. Now we need to rewrite this sigma as much as we can. We have a rule to add up a bunch of 1's, and it's based on what term did we start with. Since we're starting with the first term, the rule says that this whole sum right here just becomes n. And that's it. That's our closed form definition. Now, technically we're done, but let's try to clean this up as much as we can. Order of operations says we take care of inside parentheses first. So, give myself a little bit more room. I have 3 times, this is distributive property, so n squared plus n divided by 2 plus 2n. Okay, now I want to take care of this distributive property, so I have 3n squared plus 3n all over 2 and plus 2n. Again, any of these steps, we have a closed form definition. I want to keep going though. I want to clean this up as much as I can. Here I'm adding 2 rational expressions because 2n can be thought of as 2n over 1. So to add these 2 fractions together, I have to create a common denominator. So what I'm going to do is do my 3 crosses. If you don't know what I'm talking about by the 3 crosses, I did this in chapter 1 video, so go back and check that out. Okay, so just multiply now across. 2 times 1 is 2. Going to the upper left, 1 times 3n squared plus 3n is 3n squared plus 3n. 2 times 2n is 4n, and plus just comes in the middle. Now we combine terms wherever we can. And our final answer is going to be 3n squared plus 7n divided by 2. This is our closed form definition. Which means we could graph this if we wanted to. The only modification we would have to make, instead of n, if we're going to graph it, we would have to call this x. Okay, so think about n as our input and whatever we come out would be our output for each specific n value. Okay, so again, this is an indefinite sum, so I can't just add up all the numbers in one shot. I have to do it individually. So like n equals 0, n equals 1, n equals 2, and find out what that output is for each one, and then add those outputs together to create the series. Okay, so let's do another example. It's going to be the same idea. We're going to use the sum identities to rewrite a problem, but the wording of the problem is just slightly different than this one was. Okay, so watch out for that. So in this example, we want to find the closed form for the series. Anytime you see that phrase, closed form for the series, what that means is we're going to be using sigma notation. So we're going to have our sigma. And now what we need to do is figure out what variable we're going to put down here on the bottom for our starting term. Well, looking at our sequence, g of n is going to be our sequence. So the input for our sequence was n, so that's what I want to use for my starting variable. So n equals. Now, what term do we start with? Well, we're plugging in n equals 0. So n equals 0 into our sequence. Now, I get to choose whatever variable represents the ending term that I want. I'm going to choose x. So I know in the previous videos and even the previous example, we typically had k here and n on top. That doesn't really matter. The only reason why I'm using n here on the bottom is because the input of my sequence had a variable n. You can think of this output as y, but I'm looking focused on the input. The input was n, so that's what has to be down here on the bottom. Input n. Now, instead of g of n, I'm going to replace it with 4 plus 2n. So I have the sum from n equals 0 to x of 4 plus 2n. 4 plus 2n. That's our sequence. We want to find this indefinite sum. Now it's very similar to the problem that we just did. We're going to create a closed form definition for this indefinite sum. Because if we wanted to graph this the way it's written, you couldn't do it. So we need to create a closed form definition. So again, I have this sigma of the sum of two sequences. So I can split that up into two sigmas. So let's do that. Again, our starting position stays the same. Our ending position stays the same. Plus goes in the middle. The first sequence goes with the first sigma. The second sequence goes with the second sigma. Now we're ready to start splitting these up, or keep going, I mean. All right, I don't have a rule for adding up a bunch of 4s, but I do have a rule for adding up a bunch of 1s. So I need to rewrite 4 as 4 times 1. And then 4 can be thought of as a coefficient, so it gets to come on the outside. So 4 sigma of n equals 0, that's our starting position, to our ending position of 1. Again, 4 is a coefficient, so it's just going to keep coming down. Now we're trying to rewrite this sum right here, the sum of a bunch of 1s. We had a rule for that, and it's all based on our starting position. Our starting position is the 0 term, so this sum becomes in x plus 1. All right. Now we're ready to go down and try to do something with this sum. Again, 2 is a coefficient, so it's going to come on the outside. And our starting position was 0, and we go to the x position. We don't know what x is. N is left on the inside. I had a rule to add up a bunch of unknown numbers. That's called the think-Gauss identity. The coefficient just comes down. So the think-Gauss identity is just x times x plus 1 divided by 2. Okay, so now I have my closed form definition. Closed form definition means you no longer see the sigmas at all. So we technically could graph this as it's written, but let's try to clean it up as much as we can by just doing some simple arithmetic. So here we have distributive properties, so 4x plus 4. Here, order of operations, let's take care of inside parentheses first, so plus 2 parentheses x squared plus x divided by 2. Now we want to take care of this distributive property. Actually, if you look at it, 2 and 2, 2 in the numerator, 2 in the denominator, these are going to cancel out. So I'm just left with 4x plus 4 equal, or plus, I should say, plus x squared plus x. Now we want to combine like terms wherever we can. x squared plus 5x plus 4, and that's our closed form definition. Which simply means we could obviously easily graph this. Our input is now x. When we graph it, whatever comes out is going to be our output. And so we could see how the series behaves over a given amount of time. So since it's a quadratic, it's going to fall down in the middle. It's going to have a max. It's actually going to rise and fall. Okay, it's going to be a max. So actually, let's graph this and see what it does. The series over time. So our x is our input, our turn position. So let's go to y equals and graph this. X squared. Now you don't have to graph this. I'm just doing this kind of as a bonus. Let's graph it. And so what's happening with the series over time is the values of the terms will fall and then start rising back up again in this particular sequence. So we can actually, once we have the closed form definition, we can see how this sequence is going to behave over time. And then we can also use that to calculate specific outputs to start calculating the series, which is just simply the sum of the sequence. And that's it for this video.